Your RAG should know when not to answer. This is the workflow you'll know how to run when we're done, which indexes knowledge, calibrates confidence, and refuses to answer when retrieval evidence falls below a threshold. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. RAG systems can sound very smart and still invent facts. That happens when the generator is given poor or irrelevant retrieval evidence. In practice, teams build abstention into their pipeline, so the system either asks for clarification or refuses, instead of hallucinating. Success looks like fewer wrong answers and higher user trust, even if the system sometimes says or do not know. This trade-off matters for help desks, internal knowledge bases, and any place where a wrong answer is costly. At a high level, abstention thresholds compare how much evidence the retriever finds against simple guards. We will use a tiny toy corpus and a few rules to show the idea. The goal is not perfect math. It is a clear decision rule: when to proceed and when to pause. We will build a minimal pipeline that retrieves the best document, measures signal strength, converts that into a calibrated confidence, checks support across top results, and then decides to answer or abstain. This lets you see each decision point and tune a small number of knobs before you ever connect a large generator. First, a tiny lexical retriever. This snippet performs the smallest possible retrieval by matching query words to document words. The variable docs holds 3 tiny documents, each tagged with an identifier, and Q is the user query. The function score computes the fraction of query tokens appearing in a document, which acts as a simple evidence score. The code then selects B, the document with the highest score for Q, using max with a small lambda. Finally, it prints the identifier and the numeric score so you can see what the toy retriever prefers. The printed best ID and score show which document is selected and how strong the lexical match is. Next, add a refusal rule for weak matches. This example adds a refusal rule so the system says no when retrieval is weak. The variable WQ is a query that does not match the toy corpus, and S takes the best score across all documents using the earlier score function. The variable min evidence defines a minimum acceptable signal. If S falls below it, abstain becomes true. This is the simplest form of RAG abstention, cutting off low evidence answers before a generator can hallucinate. Raising min evidence makes refusal more frequent but safer. Lowering it allows more answers, but risks confident guesses. The printed abstain flag and evidence confirm that the system correctly refuses a zero-signal query. Now, we calibrate raw scores into a smoother confidence. This code compares top results and turns raw scores into a calibrated confidence. The variable R holds all documents ranked by the earlier score function, letting you inspect both the winner and runner-up. The function calibrate uses a logistic curve via Python's math.exp to map the raw evidence into a probability-like value P, which is easier to threshold consistently across queries. The variable gap measures how far the top document score is from the second, catching ties or ambiguous retrieval. Increasing A sharpens the sigmoid and makes P rise faster. Adjusting B shifts the midpoint. The printed top gap and pconf show separation strength and the calibrated belief. Next, require multiple supporting hits instead of a single lucky match. This snippet adds a pragmatic guardrail that checks whether enough top results support the query. The variable R holds the top K candidates by score, and support counts how many of those meet a small per document threshold. Requiring at least 2 supportive hits reduces the chance that a single noisy match drives a confident but incorrect answer. You can raise K to search wider, or lower the support threshold to be more permissive. Both changes directly affect how often the system proceeds versus abstains. The printed support tells you how many documents cross the bar, which signals whether evidence is concentrated or sparse. Finally, combine the checks into a decision function. This example assembles a minimal decision policy that refuses weak evidence and falls back gracefully. The function decide ranks documents, computes a calibrated confidence P with the same logistic form, and evaluates 3 checks: the confidence threshold, the top 2 gap, and a top K support count. If any condition indicates uncertainty, it returns an abstain action and a lightweight clarifying prompt rather than guessing. Otherwise, it returns an answer that cites the winning document and its text, ready to feed a generator. Tightening thresholds increases refusals but boosts trust. Loosening them does the opposite. The printed action and answer show whether the query is handled or safely refused. In a real project, this same policy maps directly to production. Swap the toy lexical score for a vector retriever, keep the same calibrated confidence step, and run the same top K and gap checks before sending context to your generator. That keeps the decision logic simple while you scale the retrieval backend. Recap: it is a small retrieval plus simple checks that decide when to answer. Use it when hallucination is costly, and you can tolerate occasional refusals. One caveat is that stricter thresholds reduce coverage and need tuning against real user queries. Next step, tune the confidence sigmoid sharpness and the minimum evidence threshold on a held-out set, so you can hit your desired balance of precision and coverage. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.